I would like to thank you, Shafique, for accepting this invitation. So today, the talk, it will be around the energy efficiency and security for TinyML and EdgeAI. Shafique will talk to you today about the cross-layer framework with the hardware and software techniques. So let me first thank you again, Shafique, and I will, let's say, introduce you to the audience here in TAI. So Professor Shafique, so he's currently working on NYU Abu Dhabi. So he received his PhD in computer science from Karlsruhe Institute of Technology in Germany, 2011. Afterwards, he established and led a highly recognized research group at the KIT for several years, as well as he conducted an impactful research and development activities in Pakistan and across the globe. So besides co-founding a technology startup in Pakistan, he was also an initiator and team lead of an ICT research and development project. He also established strong research ties with multiple universities in Pakistan and worldwide, where he was being actively co-supervising various R&D activities and student research thesis since 2011. So for sure, this resulted in top quality research outcome and scientific publications. So prior to KIT, he was with the, let's say, Streaming Networks PV Ltd company, where he was involved in research and development of of video coding systems for several years. And in 2016, he joined the Institute of Computer Engineering at the Faculty of Informatics at Wien and Technical University of Wien in Vienna and Austria, as a full professor of computer architecture and robust energy efficient technologies. So since September 2020, he used to be he integrated the division of engineering at New York University here in Abu Dhabi, and is a global network faculty at the NYU is Tandon School of Engineering in New York, also in USA, and he is the co-director of the eBrain Research Lab, and he is also a co-PA and investigator in multiple NYU Abu Dhabi here research centers, including the Center of Artificial Intelligence and Robotics, CAIR, the Center of Cybersecurity, CCS, the Center of Interacting Urban Networks, and the Center of Quantum and Topological Systems. So thank you again, Shafique, for accepting our invitation, and the talk is yours.
Thank you very much for the kind and long introduction. And I highly appreciate your kind invitation. So I hope that I'll try to give you a sneak preview of my research along the embedded machine learning, covering different aspects of designing TinyML, EdgeAI kind of systems from both energy efficiency and security. I'll go a little bit details of a couple of works, but then I'll give you a bit overview of multiple other projects that I'm working on. The work that I'm going to present you today is basically done jointly at my group in TU Vienna and as well as at NYU Abu Dhabi now. So I still hold a research group and research lab in TU Wien. So that's what this is like. They work from my complete group. It's here. So when I started, when I joined NYU Abu Dhabi, then I basically, since then I'm establishing the new lab, which is called eBrain Lab. So you can imagine this is like an embedded brain. And the overarching principle of this is like we try to embed cognitive skills inside various different embedded computing devices ranging, that are deployed in many things of IoT and cyber physical systems. Just for the ease of my bandwidth, I'll turn off the video now. If there is any question, then we can take it at the end. You can also drop it in Q&A, and I'll try to give you an overview within the next 35 to 40 minutes. But before going that, I want to tell you about what is the bigger impact of all the research that we guys are doing nowadays in AI. So, if we look at the human age, typically what we can partition into three big phases. One is the age of power, where, the nations which were having the highest manpower, skill and strength, they primarily ruled the world. Then we entered into the age of resources and industry, where the the countries which have the largest resources and the natural resources kind of stuff like fuel and advanced in the industrial technology, had the industrial revolutions kind of stuff. They primarily ruled the nations, or led the nations as developed countries, and then also controlled a lot of economic politics. But what we are seeing now is primarily the new age of data and AI, where data is the new fuel. You might have seen that the biggest enterprises in the world who are generating the biggest revenues are the ones which are holding the control on most of the data. This data is then directly or indirectly influencing many different political decisions and economic decisions. And then there is a race in innovation in the technology, and then there is also a nationwide race in the dominance in AI, because AI has been now shown to, or in general at the moment mostly machine learning, but stepping forward towards really AI. They are like the countries want to have leadership in the cutting edge technology and artificial intelligence and various different applications which are being used because of that, so that they can for example step forward in the race of the developed countries. And this is also the right moment where various countries which were not technologically advanced can show their power to lead in creativity, and to lead for example in the AI-based technologies. So I'm working on many different aspects of machine learning and artificial intelligence, but in this talk I'll focus mostly on the edge applications, where we can broadly partition them into TinyML, which are extremely resource constrained, towards the broader category of the EdgeAI. So I'll talk about what is TinyML and what is EdgeAI, what are the different kind of applications. Then I'll go into details of my cross-layer design flow that our team has developed here, where we are working at different abstraction layers of the hardware and software stack. And then towards the end, I'll talk about the future research directions in which we are moving forward, and where we believe that there is a lot of work has to be done in order to really make the AI-based technologies work together with humans in real world in a safe and secure way also. So what is unique in TinyML? You can see is that first of all, this is like a unique combination of machine learning algorithms with embedded systems and the underlying hardware architectures that we talk about. And they have the capability of performing on-device data analytics at extremely low power. So whenever we talk about embedded systems or embedded kind of devices, they are subjected to stringent resource and energy constraint. And then those complex machine learning algorithms have to be realized on those very resource constrained devices. And 90% of the world's computing systems are primarily the embedded computing systems nowadays. Combination of embedded systems, hardware, and algorithm require a lot of different challenges that I will talk about in today's talk. There are many of these cases that are always on use cases, which means the devices are most of the time either on or working in a low power mode, where you have to, for example, still keep on doing some analytics on the back end. And many of these devices are also battery powered, which means that you have to be also serious about considering the energy into the design flow at the start of the design process. So if you look at this, the biggest umbrella that people might be reading nowadays, the article or a lot of research is going on is cloud AI, but that might be only 5 or 10% of the total AI systems that you will be seeing. It requires a very high-end hardware, for example, DGX 800, for example, kind of processor used for training or giving the cloud AI services. These systems have extremely high amount of memory, a lot of storage, and the applications with the model training, big data analytics, or the cloud services given to the end users. When we move a step forward, to the end user applications, most of the systems are called mobile AI or EdgeAI kind of systems. You can see them running on your mobile devices. You can see them, I'll show you some of the applications in robotics, in cyber physical systems. There we have embedded GPUs, for example, or neural processing units. These are the kind of hardware that we are trying to use. They can have few hundred megabytes to a couple of gigabytes of memory and storage also in the same range. And typically these are like end data processing devices, but typically they are still like very powerful data processing devices, and might be having continuous learning, where the system is continuously learning and inferring for several decades. For example, consider an autonomous vehicle, which is doing these kind of processing. And then there is another very big area of, a branch of, I would call as an EdgeAI, which is specialized towards TinyML community, which earlier started with enabling a machine learning on the controller. But now they're also moving towards the small scale neural processing unit, these NPUs, where we have few hundred of kilobytes of memory available and maybe a couple of megabytes of the storage device available. Now, this is typically in sensor or near sensor processing, which means that you have a smart sensor which is capturing a signal, digitizing that, and then doing some local analytics, and then giving this local analytic results or the raw data to an edge device. An edge device might be, for example, electronic control unit in your autonomous vehicle and those kind of stuff. Now, of course, we have tight constraints in EdgeAI already, and this can be an extreme constraint in the TinyML also. Now, the type of models that we map on TinyML might also be very, very small scale compute an EdgeAI model. So if you look at this, the challenges and the design methods that I would be talking in the next slides have a significant overlap in both of these regimes. And of course, considering the model complexity versus the underlying hardware capabilities, the challenges of both of these kind of systems can be extremely complex, as I'll showcase in the next slides. The applications are gigantic, like everywhere you see that the applications of embedded computing systems, nowadays they're becoming smart. We can see them. There are hundreds of computing systems deployed in automobiles. When we talk about the fully camera based or the mixed sensor based autonomous vehicles, you will see that there's a lot of different type of intelligence processing that is done there. Smart traffic control, smart healthcare, a lot of wearable devices are there. Industry 4.0 is big, where you have smart industries deploying smart sensors in production lines, smart grids and smart houses. And then robotics is a big area already itself, where because there are so many different type of robotic things that you want to have. Now, if you look at the modern systems, there is a big computing device or a board installed on many of these robotic devices. But effectively, what we want is like what we have in a human brain, So we want to have a very small scale chip deployed for a certain type of robot. And now there's a new trend of robomorphic computing, where these kind of artificial intelligence chips would be very customized towards a certain type of robot and things like this. And when they have to work in all of these systems, you will see that they're kind of critical kind of systems, because they have to be interacting with the humans, and of course they're mostly alive kind of systems. And on the other side, we have strict security, reliability, and safety constraints in these kind of systems that we have to meet. When we talk about so many of these systems interconnected in an IoT kind of framework, you will see that we have a huge amount of data being generated, and then we know that machine learning is, for example, is a proven black box processing toolbox to infer knowledge and derive predictions. And then there are also other kind of advanced learning models which can also model as a gray box kind of stuff. Just to give you an idea how much data we are talking about, this is some case studies by Intel Autonomous Vehicle Project, and you can see is that depending on different type of sensors, close to 4 terabytes of data is being generated per day. Now, on the one side, this is a big challenge for the training side, because you have months of test drives data that you have to process. But on the other side, imagine that if you have to do the inference for all this kind of data in real time, what will happen? And when we step into the content learning or lifelong learning framework, where these devices are learning on the fly on these embedded computing systems, and this becomes another big challenge for that. So I call it like as a complexity square, because we are talking about extremely big data processing at the edge, where we have so many stringent constraints. Now, going into the other challenges, we have robustness challenges, because the system has to be reliable and secure. We have performance at extreme low energy budgets, and then there are a lot of other kind of things like adaptability, privacy, and interoperability, because many of these systems, you will see that we are porting to different computing devices. So your models should fit to multiple different devices, should fit to multiple different scales. So scalability and all those kind of stuff is there. And many times you don't want to expose your model or data, so the privacy is again another kind of challenge. So if you look at this, the space of the complete design challenges are huge. And that's some multi-objective optimizations for these kind of embedded machine learning models is also getting very hot nowadays. Now, how much complexity we are talking about? Just to give you an idea, for example, many of these systems that you see here, like ResNet kind of stuff, and now the emerging natural language processing kind of models, which are based on Megatron, like transformers based, and then you have vision transformers kind of stuff. Just to give you an idea that they're like, thousands of times complex at ResNet. ResNet 50 is already very, very complex to train. Megatron, when it was trained on V100 GPUs, it was 8.3 billion parameters, and they required 512, V100 GPUs, which already you can see is that training these kind of models is out of the hand of the regular organizations, and only enterprises are able to handle that. If you look at the growing trend, the GPT-3 was 90,000x more complex than ResNet. This is the study done by Microsoft team, and you can see is that the trend is becoming more and more complex. As a embedded AI researcher, the first thing that I always talk to my team members is that there should be some kind of disruptive way of thinking about how the models should be developed in future, because just making them bigger and bigger is only feasible for certain organizations. On the other side, this does not match with the embedded computing stuff. And in embedded systems, we have also a lot of strict accuracy constraints as well as real-time constraints that we have to meet. So challenges are huge on the one side, both in terms of robustness and energy efficiency. But on the other side, a lot of times when we talk about inspiration from the human brain, there is an inherent desire to reach to the efficiency of a human brain. And when we talk about efficiency, this is the efficiency in terms of performance per power. So human brains typically, work at close to 20 watt, while these kind of systems, they are like consuming a huge amount of energy. So we are talking about 1000x to 100,000x of energy consumption, kind of stuff that we're talking about. The system that you see at working at 1 watt or 10 watt of the devices, they cannot do so much of intelligence and machine learning that are typically, for example, done by human brain also. So it's about accuracy versus efficiency. That is the challenge that we have to meet in real life. Now that's one aspect. The other aspect is about the security of these kind of systems. If you look at this, then security, safety, privacy, all these aspects are there in the robustness world. There are so many incidents which have been reported of the crashing of these autonomous vehicles. I just want to show you a couple of attacks that has been done. You can see here is that this is, for example, an attack done by a Chinese company. They bought Tesla car. They did some black box attacks. One of these attack that is shown in this thing, this is hacking into the environmental system. They just showed some kind of random patterns to the cameras of the car, and suddenly the environmental control system was activated where the wipers were moving, considering this is a rain kind of signal or not. Another experiment that they did was basically they put 3 patches on the road. And when they triggered this autonomous, like, the autopilot kind of feature in the Tesla car, then what they noticed also is that the car, for example, suddenly changed the lane and things like this. This is like just some experimental examples that I've shown, but there are so many other kind of attacks that people have done on the real mobile devices, on the real autonomous vehicles, and they have shown that it's very easy to fool modern day intelligence systems, through different type of attacks. And this is only one type of adversarial attack. There's a huge number of attacks that people can do even in black box settings. Now, just to summarize, the first and foremost challenge in realizing a TinyML and EdgeAI system is the compressing extremely complex TNN models on resource constrained devices. When you talk about resource constraints, resources are not in terms of very limited compute power, but it's also the memory power, and it's also the external memory accesses like DRAM, where a lot of energy is being wasted. So you need to optimize these systems both from computing as well as from the memory side. Then reliability is another big challenge for these kind of systems. And there are different types of reliability threats. One type of threats are permanent faults. When we are making those chips, there can be faulty components. One way is to throw those chips. Other way is that you do some intelligent optimizations to increase the yield. Other are the transient faults, which can happen due to many different sources, like soft errors. There could be voltage noises. There could be other kind of issues. And then third kind of issue is like aging, where the systems age over the period of time. There could be dielectric breakdown and those kind of technological problems. And because of those problems, the systems can be, or the components of a system can be unfunctional and things like this. The modern day practice is putting 2 different processors and doing some kind of voting in a lockstep kind of fashion, but this is super costly for any machine learning system also. Now imagine I want to have a small chip, very low cost chip in my autonomous system, in my robot or in my smartwatch kind of stuff, and this should not fail over the period of time. Then security challenges, because these systems are deployed in real world, so we can also look into different types of security challenges, but I'll go into detail of this later on. Now, there are different frameworks that are available already, which are built on top of like standard framework like TensorFlow and things like this. So there's a TensorFlow Lite, there is also PyTorch Mobile, those kind of features. I mean, like they offer certain features to compress the models. And we have then hardware accelerators, which are specialized MAC unit arrays to do the matrix multiplication kind of processing. And then there is an emerging trend of neural architectural search, integrated with pruning and quantization in a multi-objective, for example, the APQ framework from MIT and things like this. Most of these systems, if you see that they are either amenable to a certain type of model, or you need a lot of, for example, hand optimizations to go through that. So there is a growing trend of making automated design frameworks for hardware software co-design and co-optimizations of these kind of systems. Most of these systems that you see in modern worlds, they're only targeting performance and accuracy, but as I said, the challenges are a lot in terms of security, energy optimization, as well as some memory and things like this. So in our lab, we are working on various of different aspects of this thing, and this is like the joint vision from my lab in Vienna as well as in NYU. So, and we believe that there is no single silver bullet to address all these challenges. We have to address these challenges at various different abstraction level of the hardware and software stack. The first thing is really to understand for any given type of task that what kind of machine learning models are amenable to these, solving our problems. We study them on, for example, very fast way on, doing optimizations for the regular GPUs. These are the GPUs, higher-end GPUs, where we do the optimizations and explore those kind of stuff. NAS and those kind of architectures are also explored on this thing. We are extensively working on building custom accelerators. On that, we are looking into the hardware optimizations for energy, as well as the memory optimizations for that. There is a growing trend of approximate computing into this thing, where we can approximate both at hardware and software level without sacrificing the quality. We're looking into dedicated neural processing pipelines, connecting them to specialized SRAM architectures, and then also reducing the off-chip memory accesses for that. We are looking into automated frameworks for neural architecture search and network compression, considering both pruning and quantization. We are mapping on multiple different type of devices. For example, in one of the research in neuromorphic architecture, we are looking into and mapping stuff on Intel Lohi chip. On the other hand, on the more generalized GPU stuff, we are looking into NVIDIA's embedded GPU platforms. We are also looking into Intel neural compute sticks kind of stuff, and we are also looking into custom FPGA acceleration, as well as our own NPU designs and stuff. We started looking into also emerging technologies, because there are hypotheses that a human brain is like a big memory where you do the in-memory computation. So there are very interesting trends on resistive RAMs and stuff. We don't have a lot of work in this area, but we started a little bit of work in this direction, and then hopefully in the future we can grow in this direction as well, because we can see that what kind of issues can happen. But at the moment, since due to lack of the publicly available models, the research in this area is only restricted to some groups which have the access to the actual physical models and the devices. And then, of course, we can look into post-CMOS technologies, not only resistive RAMs, but also other kind of devices, which are based on CNT-FET, for example, transistors, doing the 3D stacking and stuff, and ultimately realizing an extremely compact hardware software system which can work under stringent hardware and energy constraints. So if you look at this, I just give you a bit overview of different steps of this automated framework that we are going into and working in our lab, and there are different parts of these tools are already developed and open source, and we are in the quest to really integrate many of these tools into one consolidated framework. But there are a lot of other challenges to doing to do that. At the training side, we are looking into fast training techniques. We are also looking into backdoor attacks, which are done typically during the training time at the cloud and stuff. So there are dedicated projects working on the backdoor attacks and looking into this. We are also now starting some work in the encryption to ensure the privacy, for example, homomorphic encryption based DNN acceleration and things like this. We have developed our own neural processing unit, but as I mentioned, we also looked into other kind of our hardware architecture. There are two ways to design an embedded deep learning model. So I'll just start doing maybe some annotation so that I can guide you through this diagram as it becomes complex. So the one way is that we have certain design constraints. We look into these design constraints. We have a pre-trained model that we do that we take from this pre-trained model, and what we do is that we pass it through different model compression kind of techniques, where we do different type of pruning depending upon the underlying hardware architecture, different type of post-training quantization kind of techniques, and then we obtain a energy efficient model. The other part that we are looking into is the hardware-aware neural architectural search, where we solve a multi-objective design optimization problem, and we have specifically developed genetic algorithms for that, based on NGS2 genetic algorithm framework. We take the hardware constraints, we take the security constraints in the recent work. This is another work which is under submission. We are looking into energy as well as security constraints. But a lot of these hardware and software constraints can be given to a NAS framework, and then we can automatically output extremely compact and energy efficient model. Once we have a model, once we have the given hardware architecture, we also look into other kind of compute energy optimization by, for example, approximate compute blocks that we can incorporate. We can reduce the memory latencies by having efficient on-chip memory buffers. We can approximate the data inside the buffer. We can reduce the communication between on-chip buffer and off-chip memory by having intelligent layouting of the data inside the memory and things like this. I have a couple of sneak preview of these works in this area. The whole idea of this step is like, we get, extremely compact model. Just to give you an idea, one of the pruning techniques that we have developed can reach up to 190x, memory savings for different DNNs at very, very low accuracy loss, which is only 0.1. Another of the work that we have developed on the approximations or approximate computing neural processing units, we have achieved 1.x energy efficiency and no accuracy loss. Approximate by name sounds like maybe we are having some kind of errors, but we have developed extremely intelligent compute array where we can generate self-healing approximations, which means that one component generates positive error, other component generates negative error, and when we do a accumulation operation, then both positive and negative errors can cancel out, and the net error is basically zero. The memory optimizations can, just to give you an idea, can lead up to, for example, 45% of the reduction in for very complex models. Once we have optimized hardware and optimized software, then we look into the reliability issues, because these are extremely complex problems also itself. We look at both, reliability at the software as well as the hardware level. There are various different type of reliability. I don't want to go into details of that in this talk, but we can have later on further discussions on this thing. But we, for example, look into aging errors, how we can, for example, increase the aging of a system. We can handle the permanent faults, which can happen in these neural processing arrays. We can handle the software mitigations through range restrictions kind of stuff. And many of these techniques are developed under an industrial project where we have actually delivered this output. And then, I know that some of the groups are actively using our tools and our algorithms, and they have extended and refined these algorithms to build even more robust models. Once we address the reliability issues, we also look at the security challenges at the inference side, where we are looking into the impact of the quantization on the robustness of the model. We have developed various adversarial attacks and defense mechanisms at the edge, looking into the timing problems of this. And then one of my team members is actively looking into the formal analysis of these kind of models, because formally verified model is an extremely important thing that we require for the safety critical systems. But this is a very complex problem, so we are only, you can see, is at the beginning step of this kind of stuff. And we are looking into how the model optimization parameters can impact the robustness as well as the formal analysis of this kind of stuff. So all in all, if you look at this, this is an extremely complex framework. We have different parts of these frameworks, individually and separately developed, and several of them are open source. But the long-term goal is to really build this as a single click, integrated automated framework. That would be amazing. So having said that, how much time do we have now? Just to give me a graph.
Yes, okay. Shafique, we still have 10 minutes almost. Yeah.
Okay, so in the next 10 to 15 minutes, what I will do is that I will give a little bit overview of the more detailed works that we have. And maybe I'll focus more on the result side so that you have an idea that how much savings we get from each of these techniques. So we have developed, for example, a pruning network, pruning technique where we analyze the sensitivity and remove the non-sensitive neurons, and then we can do this in iterative way. You can see here is that we can prune up to 90%, like 90% of the models, neurons can be removed without losing much of the accuracy. You can compare the A versus D, and you can still see that D has a high kind of accuracy. Then we can do the quantization. Of course, if we have aggressively pruned networks, then the quantization can also lead to quality loss. But note that after this quantization, we don't do the retraining. The retraining is only done after the pruning. So this is a post-training quantization, because training also itself costs a lot of time. But we also don't train completely. We always train only for a few epochs, to recover the accuracy. Once we have the software level approximations, we go to the hardware level approximation. We have seen that what kind of hardware architecture. You can see that on the x-axis, the various different type of hardware architectures that we have developed, non-self-healing as well as the self-healing ones. And we can see that the self-healing ones, for example, can also still give you a very high accuracy without losing, very high energy efficiency without losing the accuracy also. And we have done this study for many different type of networks. So it's not only that in one network we have the same studies. Of course, for some network, the accuracy loss can already start, at 60%. For some cases, it is at 90%. For some cases, 80%. So you can see that this highly depends upon the internal resilience of the network also, and how much retraining we pay at the end of the day. And nowadays, the modern trend is like doing the pruning quantization in one integrated framework, or even the neural architecture search together with these kind of stuff. Then just to give you an idea that in the memory optimizations, how do we achieve so much of benefits? The reason is that we basically look into the network model, and we pass it through a tool to understand and analyze the reusability across different weights, across different activations and input and output activations. And then we do not recompute or refetch those kind of data which is being reused. So we try to keep the reusable data as long as possible in the on-chip memory and reduce the off-chip memory excesses. This is one thing from where we can get 12 to 46% of the DRAM savings. Another technique that we do is basically the partitioning of the data into different tiles and mapping it over different regions of the external memory, which will then basically be making it more amenable to access. And this highly depends upon the underlying architecture of your DRAM. Like, is the DRAM is a sub-array level parallelism is supported, or only it's a bank level parallelism. So don't go into details of this hardware, but just for an abstract level, depending upon the underlying DRAM model, we can do the mapping into of the data so that we can reduce the number of accesses to the DRAM. And this can reduce up to 90% of the energy consumption. And this is a great tool to achieve high savings. Another kind of optimizations that you can do is basically across the application level. For example, can we compress the input image and then do the learning or object detection, for example, is one problem on those kind of stuff. But then, when we compress the data, then it might happen that the network, for example, loses some of the efficiency. Another growing trend is basically based on the temporal prediction, where if we are running a data on the videos, then we can exploit the temporal prediction, and then we can, for example, have some selective tile partitioning. And some of the tiles we do aggressive machine learning, and for some we can simply do a very lightweight machine learning, or can reuse the data from the previous one. For example, if it's a non-moving object versus a moving object. Then going beyond regular convolutional neural network, just to give you very quickly, we are looking into also advanced networks like capsule networks and spiking neural networks. We developed world's first framework on the quantization of the capsule networks, which gave us up to 6x memory reduction. We did the quantization of the activation functions and the weights as well. Also, we also developed the world's first fast training network, and these are then later on being picked up by the community, and different other frameworks also came afterwards, where we have first adopted and understood what are the traditional techniques, how they can be implemented for the capsules. Capsule is a very special type of convolutional 3D convolutional block, but also in the capsule networks, we have different type of operations like dynamic routing or expectation maximization to, for example, learn other aspects and do the cross coupling between different capsules. We also developed the first neural architectural search framework for the capsule networks, and these are all open source frameworks. People have downloaded and used them also in the community. And we have showcased that by running a neural architecture search, first of all, it's a very complex problem. The search time and space also increases. We can achieve, for example, more than 50 to 60% of the energy savings as well as latency reduction. And we are also looking into the security aspects and reliability aspects of capsule networks, because people have originally the thought that due to the learning of the orientation and poses, and also having the cross coupling between different capsules. They may be more robust to adversarial attacks and also the affine transformation, but we have showcased that this is not the case. They do differ from regular convolutional networks, but they have their own vulnerabilities. For example, there are special vulnerabilities in dynamic routing algorithms that make it more vulnerable for that. I can skip this slide. This is for another stuff. I can go to this slide, which is about spiking neural network. We are actively looking into the spiking neural networks as well and the neuromorphic computing things, because we want to be prepared that if this, for example, to be proven for the community, then what are the best practices that can, make them reach the end products very fast. So we are looking into, for example, efficient mapping on neuromorphic processors based on the DVS, for example, signals. So the DVS cameras do not capture regular images, rather they capture the change in the images. So these are called dynamic vision sensor, which generate spikes, and those spikes can be given directly to the spiking neural network. We have looked into, for the regular networks, we have looked into the autonomous driving certain use cases, and now we are working actively on the spiking neural network and their use cases in the ADAS stack. We recently developed a full-fledged spiking neural network, which is able to do, for example, background prediction versus an autonomous vehicle, let's say a car prediction in an autonomous vehicle use case, completely based on the DVS camera. We are also looking into various different optimization framework to enable embedded spiking neural network or embedded neuromorphic computing, where we are looking that the optimizations done for spiking networks are completely different from the done for the convolutional neural networks. For example, we can have, lateral inhibition, self-inhibition kind of stuff. We can have spiking quantizations. We can, for example, have different type of, selection of the weights, as well as also the synaptic weight decay and those kind of principles that we can deploy on this thing. We're looking into the resilience to, for example, DRAM errors, to compute errors and things like this. We're looking into the continual learning frameworks, because one of the limitations of these spiking networks is that their learning algorithms are either very, very complex or not as efficient, when they are deployed in real-time learning kind of frameworks. We are looking into the content learning framework, which is good for unsupervised learning, but with embedded constraints. Like, we don't want to have we don't want to have them extremely complex. Rather, we want to have them resource and energy efficient. And we have also developed the first quantization framework for the spiking networks, where we achieved like significantly high memory savings and stuff. I'll give you these slides. You can have them also in your local system, so that you can go through them in more detail, and then we can discuss maybe more in person later on during some other future visits. We are also actively looking into the spiking neural network security issues. So I can skip easily them. We have done, for example, some analysis of the spiking training parameters on the robustness. We recently have one of the first attacks on the dynamic vision sensors in a robotic use case of autonomous vehicles, like it's the mobile robots kind of stuff, which was published by IROS kind of stuff, and also actively, looking into some more advanced kind of attacks on them. We have also looked into counterfeiting, fault injection attacks in this thing, and we're also looking into other kind of adversarial attacks. In the application point of view, we deploy mostly in autonomous vehicle use cases, as well as the smart surveillance use cases. But we are also looking into the wearable healthcare use cases. This is a project that I am currently working in one of the European, large-scale, Excel projects. We are looking into, for example, biosignal processing. I quickly skip through that. One of the interesting works that we have recently done is building a custom neural architectural search framework with integrated with the model compression tools, where we have showcased that we can generate many different Pareto points for different type of constraints in only matter of few hours, compared to, for example, months of training and things like this. And for example, one of the Pareto solutions have obtained up to 53x reduction in the hardware overhead at a very low quality loss. And this is only the loss in the accuracy, but we have also studied that the loss in actually the application output, for example, detecting certain spikes and stuff in ECG signal or EEG signal, those were pretty accurate. So we did not get any much difference in the false positive, false negative compared to the accurate golden signal processing also. In one of the EU projects, we are looking into working together with Philips Healthcare and TU Vienna. My group in TU Vienna is working on that, where we are building a handheld ultrasound device, which you can see an example here, but the actual device would be different from this. This is a device which the ladies can buy and use at home, and don't need to go to hospitals all the time. And what we are looking into is like data generation, phantom data set generation, looking into custom embedded AI algorithms, which can fit into very small scale devices that can fit into very, very tiny, single hand kind of object. And then looking into hardware acceleration for that, and doing short-term, long-term prediction of the fetus, which are very, very accurate. So this is done, of course, together with the hospitals and other stuff, but our direct interface is the Philips Healthcare in this project. Looking into very complex problem, but interestingly, those problems are all embedded in the nature, and they have to be, of course, having highly accurate kind of stuff. So this is like, pretty much close to end of my talk. So I just give you a sneak preview of that. In our lab, we are actively looking into various different security research aspects. We are looking into adversarial attacks on machine learning. We are looking into backdoor attacks on machine learning. We are looking into privacy attacks on machine learning. I recently got a paper on DNN obfuscation at IGCNN, for example. We're looking into custom hardware trojans specialized for the neural, processing units kind of stuff, and looking into side channel attacks. Most of my research have been on backdoors and adversarial, and we're stepping forward towards privacy preserving ML and things like this, particularly in this area, which I believe is a great topic to explore, to be explored for the modern neural networks. We are also actively looking into reliability aspect. I skipped this slide, but just to give you an idea that there are so many different type of threats where we need some custom hardware support for not only the mitigating the permanent faults, but also we need a lot of software support and runtime support to mitigate the software rates, for example, to detect online permanent like faults which come over the period of time to aging and become permanent, or from intermittent to permanent. Looking into, for example, certain transient errors and try to, for example, devise certain software level techniques, for example, defining the bounds of certain activation functions, activation values, range restrictions of that, formally deriving the noise tolerance of these kind of networks for a certain type of noise, and then ensuring that we can give you certain confidence and guarantees and some certifiability on top of that. And this is extremely important thing whenever you have to deploy anything in the real system. I did not put any of my work in reliability and security and the formal verification in detail because those itself are very, very big topics. And we can have separate discussions or in-person meetings in your group later on those topics. Now, so closing my talk, what kind of future challenges which are still there? There are new computing paradigms coming, in-memory computing, approximate memory computing, different type of brain-spared computing, but as well as also different machine learning models are coming. So we need to look into them and see that how we can get the best of the both worlds. It's not always about deep learning or convolutional neural networks. It's about many different type of machine learning models, spiking models, which can be good in different scenarios, especially when we're talking about for example, asynchronous learning, event-based learning, and content learning kind of frameworks. Optimization framework needs to be automated. They need to consider multiple objectives in one single integrated optimization loop. We need better techniques for training and optimization so that we can cut down the cost of these trainings, and models which are amenable to train fast and in real time, so that we do not have dependency on very, very big GPU machines, and break that kind of deadlock for regular organizations for this. Other aspects of models, interpretability, explainability, fairness, and robustness, these are all still there itself, very, very big areas. But now people are looking into conjoint optimizations of interpretability, fairness, and robustness through new mathematical foundations. For example, can I give some kind of causal reasoning of these deep learning models, which can make them not only robust, but also explainable, and then we can build on top of this. Formal analysis and verification is a very complex problem, and this is the reason because most of these models that we're talking about are on the one side probabilistic, but they have a very wide range of data values, and most of the standard type tools for formal verification, they run into scalability issues. So we have practically seen those problems, and we are looking into how to solve those kind of problems for that. In summary, AI is a big area. We, at the moment, currently only looking into very small subset of those problems in machine learning. I would say that the applications are wide range, and with this explosion in the machine learning and AI technologies, I think they will be everywhere now, and there is no escape from that. And we have to, really engineer them from various different aspects of throughput, energy efficiency, and robustness. And the key is to engage various different experts in machine learning community, as well as hardware, software, system level design, people designing for dependability, people designing for safety, people designing for security and energy efficiency. They have to come on board to come and make real practical systems, and not only solving one problem which leads to other problems. For example, a highly performance efficient system can be extremely vulnerable to security attacks, or an energy efficient system can be vulnerable to maybe also reliability and security threats. So you need to cope with that. So towards closing, I want to just give you an idea that there is a growing trend of lifelong learning, which means a system deployed in the real world is subjected to unpredictable scenarios. So one shot learning will not help you in any case. So there is, for example, one of the large-scale DARPA initiative of lifelong learning. There are NSF initiatives on real-time learning. There is a content learning framework already there. So people are talking about that in a few years, much of what we consider AI won't be AI without lifelong learning. A system has to learn over the period of time, throughout the lifetime. Imagine an autonomous vehicle deployed on the road for 20 to 30 years. And you know that, the security guys can come and tomorrow propose another attack. There can be unpredictable scenarios coming in the drivetrains and those kind of stuff that we will face. And robotics are anyway looking into those kind of stuff. So this is one of the, I think some of the, this is one of the labs in NYU. I don't know if you can see the video or not. Somehow this is not playing here in my hands. Yes, this is called Kinesis Lab. The Kinesis Lab is basically a joint research facility and research and engineering facility in NYU Abu Dhabi, where there are a lot of different type of autonomous systems, different type of robots, different type of engineering stations are there, where we can go and build and test our intelligent solutions on the field. They range from various different type of unmanned aerial vehicles to also the unmanned ground vehicles. Just besides behind this thing, you can see this free space. This free space is also my additional autonomous systems laboratory, which I'm building and hope to build, in the next couple of years. And this kind of framework and facility allows us to test our technologies in real world scenarios and understand the actual practical constraints of the systems, both in terms of, of course, safety and reliability, as well as also from the real-time performance and energy efficiency. So the long-term goal is that we try to, for example, realize some kind of coordinated autonomous systems with heterogeneous devices, which can learn, in real time, and can also, for example, solve real practical problems of the world. For example, reconnaissance, distributed slams, and things like this. I would like to acknowledge my team here in Vienna, and also my collaborators worldwide. All the work that I've showcased you is really a small subset of the work that is done by my team and also my students across the globe. Thank you very much. I'm here as long as you want now for your Q&A. And so feel free to unmute yourself and raise your questions, and that's it.
Thank you so much, Professor Shafique. So there will be, some questions, in the session. So the first question, is TinyML in general a type of distributed learning? If yes, is it federated or decentralized?
So TinyML is a very broad area. Any system which is very extremely small scale, where you don't have extreme, high compute power, that's come under the TinyML stuff, where I showed you that it has only, limited, or let's say few compute blocks, maybe hundreds of kilobytes of memory. Now, a TinyML system can do a local learning on one single device, or many different TinyML devices can be put together to do a collective learning, in a distributed learning framework, like federated learning and those kind of stuff. So TinyML has many different use cases. One of them could be distributed learning, but there are many different cases of local learning as well.
Okay, good. So the second question, they are asking if you can provide a reference to use the capsule network research that you mentioned during this presentation also.
Yes, so capsule network actually was originated from the Google Brain team. The Hinton actually was one of the person who started this thing. So they have their couple of capsule models which are openly available, and there are then other like capsule models came like deep caps kind of stuff. So further models came also. And then it's not only the capsule model, it's also their coupling models. Like, one is like dynamic routing, other is expectation maximization. And now people are coming with more advanced coupling things where they can have better coupling and learning of the orientation and poses. Of course, drop me an email. I'll send you a couple of links of the papers and online models which are available. But just to give you already heads up, the biggest issue with the capsule network at the moment is the training time. So the beauty of capsule network is that they can have better learning compared to convolutional network for a very small set of training data sets. Okay. For complex networks, you need a big data set. Capsule networks can learn from very small data sets because they can learn a wide range of features. Not only the local features, they can also learn the cross coupling between the features. But the problem is that the training is extremely complex. So that's why they are not very famous in the products at the moment. But on the other side, there is a big research going on in making them fast, making them training fast and lightweight and doing this thing. So drop me an email. I'll share some models with you, like links of the models, and then you can definitely, or I'll connect you even with my student who is actively looking into this. So we have worked on the CapsNet model from Google Brain team. We have worked on the Deep Caps, model from another group, which is openly available.
Okay, is there any other question, or I have some questions, me too. I don't know if you have other questions for the audience. So yeah, I will try to ask two questions. Meanwhile, if you have any question, you can put it on the chat, and I will
there is another question about TinyML on ST32MCU. I don't recall that, but I know that there are. So the full TinyML community has a lot of portfolio. I can refer to you to the TinyML webpage where you can look into all those examples. It's just that this is has grown so big that I don't remember all of the stuff, but I do believe that ST is actively working on this thing. They're one of the partners in this consortium kind of stuff. So, so I can point you to the TinyML forum, and they have the complete portfolio and stuff written on there.
Okay. So I have one question, Shafique. In fact, dealing with such issues and solving such AI, or running such AI complex algorithms requires for sure a multidisciplinarity approach that will cover different level of abstractions. From software to algorithms to the architecture itself, and also the micro architecture and the technology. So have you considered such dedicated platform or designing such dedicated platform for such applications here pertaining to the neural architecture search, if you have considered that in your works?
Okay, just to clarify, are you asking about have we considered an automated software framework or a specialized chip?
A specialized chip.
Okay, so we started working on a neural processing array, but designing a hardware chip is a very, very complex problem. So in Vienna, I started doing that. We do have a small RTL model and some of the FPGA prototypes of other kind of stuff. But when I joined NYU Abu Dhabi, one of the main goal was also under Center of Cybersecurity. We do have availability of multiple hardware engineers and some fabrication kind of budget for that. So in the next couple of years, my goal is to build a robust neural processing chip where we can even employ hardware security principles, so that you cannot even, for example, hack them, or you can do inherent encryption and things like this. So I am on to that. Let's put it like this. But I do believe that we need some dedicated neural chips. You see that even in your GPUs now you get tensor cores. Those tensor cores are primarily systolic array-like architectures. We have TPUs like tensor processing unit from Google. We have neural processing unit from every company like Alibaba, from Samsung, from all those companies. So I think neural processing unit is the way to move forward. But considering not only the performance but also the security issues, we need to have multiple of those things at the hardware level, but also at the software level, because once you have the dedicated chip, you need the software tools which can map your system very efficiently on that. And it's not only about mapping, it's about designing even a machine learning model which is amenable to your actual hardware. And this is what is the long-term goal that I was talking about. But of course, there is a need for such kind of chips and we need tools to make those chips usable.
I see. Okay, so okay, I have another question, Shafique. I mean, here you are when you are binding your TinyML. So you confirm that you are not like using a dedicated US with, let's say, a minimal set of services that allow an efficient binding of the TinyML on the hardware platform. So you are working on that right now, as far as I understand, right?
You're talking about mapping a small model into a small system. Yes, this is something. So for that, there are two paths to do that. That's what I was asking. If a model is given to you and we have to map on a TinyML device, that can be, for example, an NPU stick or like neural stick. For that, the standard way is to go with model compression techniques like doing aggressive pruning, quantization, and doing this in automated flow, where you can give the feedback that how many processing units I have, how many flops I can support. And then once you reach a solution, then you map that thing there. Other thing is that we also look at the memory and then try to reduce the memory so that we can get more speed up from this. Now, this is one path to do that. But as I said, now the modern trend is that the reason why is that because by doing this, you cannot get a model which can have a high accuracy as well as the real-time performance that you need. Sometimes you just don't find that solution. So another growing area is hardware-aware neural architecture search, where I can feed this TinyML device constraint inside the neural architecture search algorithm, and then it should output some algorithm, some model architecture, which is amenable to that device. Okay, so we do both actually.
Okay. Another question from the audience, they're asking if you can give them an example of application of TinyML on STM32 MCU.
Yeah, this is what I said, that I don't remember exactly, but I can point to you to the TinyML forum. They have many of these kind of things,
Okay, no worries.
So for tinyml.org, I guess. If you just go there, you will find many of these things,
Okay.
Good. Every company, even let's say even ARM has a big project on TinyML, starting with the compilers and all this thing, And even I think their ARM's TinyML framework is even open source.
Good. Okay. Okay. So I don't know if you still have a lot of questions. I mean, the audience.
I mean, I would love to actually visit you guys, because I think meeting in person, you can do much more interactive discussions and stuff, That's
Okay. Okay. So if there is no further question, I would like to thank you again, Shafique, for your time for this nice talk.